Hello and welcome back to our solution papers for Fastpapers. So today we're going to go through the Cambridge International AS&A level examinations for paper 2. Hopefully you guys had a good exam. The questions weren't too difficult or anything that was out of the syllabus, and I'm sure you guys are well prepared for everything. So we're just going to go through the paper very quickly and we'll see what the answers you're expected to write are, and if you have any questions, feel free to contact us and we'll be sure to help you out. So let's just jump straight into it. So the first question we have is, elements in period 3 of the periodic table show trends in their properties. So complete table 1.1 by identifying the lattice structure of the crystalline solids of magnesium, silicon, and phosphorus. All right, so first let's go ahead and take a look at what we've got. So we've got magnesium. So this is obviously a metal. We have silicon, which is a metalloid. So it has both metallic and non-metallic properties. And we've got phosphorus, which is a non-metal. So when we begin with all of this, so whenever you're dealing with a metallic structure, obviously you're going to have a giant metallic structure, giant metallic, and then you're going to cap it off by writing giant metallic structure. So for those of you, I'm pretty sure you already know this by now, but still, just to refresh our memories, you have a lattice of positive ions. This is for metal, obviously. I'll write that down sooner. So in case anyone's going through the paper, they won't be too confused when they see what this is, but I'm pretty sure all of you know by now what this is. So this is your metallic, what the structure in metals look like. So you've got all these positive ions, and they're surrounded by a sea of delocalized electrons. And the reason that metals are able to conduct electricity or conduct heat is because of these delocalized electrons. So they're very efficient charge carriers. They're very efficient at carrying heat as well. So this explains why metals are both good conductors of heat and electricity. So I know that's not part of the question, but still a good idea to have all these concepts in mind whenever you're going through any question, because then you'll be able to relate this to, let's say maybe there's a question down the line where they're talking about it. So this is your metallic structure. So it's good to keep in mind. So the delocalized electrons. And also a lot of questions, sometimes they'll ask you to draw out your, let's say the structures. So these help to visualize and to sort of give more substance to your answer. So you can write down they conduct heat plus electricity. Electricity. So good to know, and obviously you're going to label this positive ions. So moving on, we're going to go to silicon. So silicon is interesting. So the way silicon is structured is, I'll use a different color for this, is you can think of it as a tetrahedral molecule. So what that means is you got one silicon atom. So let me just scroll up a bit. It's bonded to 1, 2, 3, and 4. So this is what a silicon molecule looks like. So this is silicon. So it's sort of different from your simple molecular structure. This is repeated multiple times. And so you've got yourself sort of a giant molecular structure. And that's what contributes to sort of its high melting and boiling points, right? So compare that to something like phosphorus, which we're going to get to in a minute, which is simple molecular. So we're going to write down over here that sort of silicon is giant molecular structure. You don't have to write structure, but you can just write giant molecular. So here's the thing, you might be wondering, how do we use silicon in semiconductors because of this? So we know that the delocalized electrons for silicon are the ones that are able to conduct electricity. So how is silicon able to? So the thing is that once you heat silicon to a high enough temperature, you're sort of freeing up the electrons, which are then able to conduct charge. But they conduct that electricity at very high temperatures. So it's not something that they do at, let's say, normal temperatures. In fact, at normal temperatures, silicon is almost an insulator. So you need to heat it really high, or you can add a different material to it, a conducting material to it, which increases its conductivity. So just a bit of a fun fact for you guys. Next, we've got phosphorus, and of course, very easy. This is going to be simple molecular. And there you go. You've got 3 easy marks right over there. So let's move on to the next question. The relative electrical conductivities of the period 3 elements are shown in figure 1.1. So we've got a graph over here, and it's showing the electrical conductivity. So you've got sodium starting here. It increases at magnesium. It goes all the way up at aluminum, but then we see a sharp dive as you get to silicon, and then practically we see the electrical conductivity negative over here. It's basically non-existent. So you can see silicon, it has a bit of electrical conductivity, so it's not as good as sort of a metal because it is it has metallic characteristics, and I mentioned that before, right? But you can see it's very low compared to a metal like aluminum or magnesium and sodium. So we're going to mention why there's an increase in conductivity from sodium to aluminum and why phosphorus, sulfur, and chlorine are non-conductors of electricity. So the thing about silicon is because the question doesn't mention it, you don't have to write about silicon over here. So the information that I was telling you previously, you don't have to really remember that. That's sort of like a fun fact if you just want to figure out why silicon has, even though it doesn't have the delocalized electrons, why it's able to conduct electricity at this point. So the way you'll have to mention this is that let's begin with their names. So sodium, magnesium, and aluminum have a giant metallic structure. So because they have a giant metallic structure, and I went through this previously, the structure sort of looks like this, right? Where you've got delocalized electrons that are able to conduct both heat and electricity because these are free to move. So you see, by being able to relate sort of this first question, the giant metallic structure, we're able to answer the second question over here. So sodium, magnesium, and aluminum have a giant metallic structure. You can give a comma. This means they have delocalized electrons. And because they have delocalized electrons, these electrons are able to move about freely, through the lattice and conduct electricity, conduct charges, and therefore conduct electricity. So very simple, nothing too complicated. We've got a 2-mark question over there, and let's move on. So let's go down a bit over here. So again, like I was talking about silicon, I feel like I should mention another thing, like the giant metallic structure, no free electrons. It can conduct a bit at high temperature, but otherwise, because it lacks the free electrons, delocalized electrons, it's not going to be able to conduct electricity as well as, say, your other metals. So let's move to the next question, C1. So the third ionization energies of the period 3 elements are shown in figure 1.2. So over here, we're seeing that sodium has a high ionization energy, magnesium has an even higher one, and then it suddenly drops in aluminum, rises silicon, falls against phosphorus, and then you see sort of a slow increase. So this is interesting. So let's see what the question says. Write an equation including state symbols to represent the third ionization energy of argon. So first, let's get our definitions underway. You guys probably know what ionization energy is, but just to refresh our memory, it's the energy required to remove an electron, one electron. So this is important. One electron, but we're not done with the definition yet. One electron from an atom. If you write this as part of the definition, if it's 1 mark, you're getting 0. But if it's 2 mark, you're getting 1 mark. And where's your other mark coming from? In its gaseous state. So this is a very important clarification that you guys have to remember, that it has to be in its gaseous state. So what that essentially means is, if we're writing the first ionization energy, so let's say the first ionization energy, so let's say, for example, for argon. So argon would go like this, and then it's in its gaseous state, and you give an arrow and give argon, because you've lost an electron. So electrons are obviously negatively charged. Negatively charged. So because they're negatively charged, when you lose an electron, argon becomes positive. And remember, it's still in its gaseous state. And then you're going to give plus 1 electron. So over here, what's bolded is third ionization energy. So if this is your first, your second ionization energy, you're going to have to assume that it's going to be argon, which has already lost 1 electron, because remember, you're removing a second electron. So this will be Ar2 plus gas, but remember, you're still removing only 1 electron, so this will be plus E. So that means that your third ionization energy will be argon 2 plus, again, remember, in its gaseous state. You give the arrow, and because it's the third ionization energy, you've lost 3 electrons total, still in its gaseous state. And remember, the definition itself says 1 electron. So this will be 1 electron. Next question. The differences in the values for third ionization energy shown in figure 1.2 are due to differences in strength of attraction between the nucleus and the outer electron of each ion. So that's interesting. So state 2 other factors. State 2 factors that affect the strength of attraction between the nucleus and the outer electrons. We know that the nucleus sort of is a bunch of positive charges. So let's say if there's 4 protons here, and we're going to have 1 outer shell. I'm going to use crosses to signify electrons over here, and then 1 over here. So because these are positively charged, so I'm going to give a positive over here. And let's take our other color and let's mark it negative. This is negative, 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 negative. So there's an attraction between these electrons and the positive nucleus. And it's due to this sort of attraction that it becomes more difficult or easier to remove an electron. So the closer the electrons are to the nucleus, it's going to be more difficult to remove it, right? So we're going to mention that over here. The ionic radius. So what the ionic radius is the distance. You don't have to write this, I'm just writing it for your guys' sake. Distance of the outermost electron shell, electron shell from the nucleus. Very simple. So what that basically means is, if I go down over here, this is your, let's say that, and let's say you've got 1 electron here and 1 electron here. So the ionic radius for this element will be, for example, 4 nanometers. So that means, and then let's say we've got another nucleus here. So let's say this has a bit more. Let's say it has around 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Let's say around 12. So 1, 2, and 3. So over here, the ionic radius is more. So this will be around, let's say, 8 nanometers. So this has a stronger attraction. So this one over here has a stronger attraction, and this one has a weaker attraction. But attraction aside, the ionic radius is low. So this will be low ionic radius, and this will be a large ionic radius. So hopefully you guys are able to be clear on what ionic radius is. And then we're going to talk about the nuclear charge. So basically that means the number of protons in a nucleus. So the more protons, let's say, for example, so this one only has 4. And this one has 3 shells because obviously, so it has 12. This has 4. But what happens if there was 1, 2, 3, 4, 4, 5, and 6? So remember, each outer shell after the first one can carry 8 electrons. So that means that the attraction will be here and here. So here the ionic radius is still 4 nanometers, but the number of protons is increased. So this has a stronger attraction as well. So this will have the strongest attraction. Strongest, let's write attraction over here. Attraction strongest. Because this has 6 protons compared to 4 over here. So even though the ionic radius is the same, the number of protons also affects the strength of attraction. So we're going to write over here the nuclear charge. So now we're going to use figure 1.2 to suggest the most significant factor that determines the size of attraction between the nucleus and the outer electron. So let's take a look at what's going on over here. Let's scroll up a bit. My bad, sorry about that. So sodium has the second highest, magnesium has the highest, and then we're at aluminum. So remember that this is talking about the third ionization energies. So if I were to go to sort of a fresh page, let's say over here, sodium has a proton number of 11. Magnesium has one of 12. And aluminum has one of 13. So after the third ionization energy, for the third ionization energy actually, for third IE, sodium will have 9, magnesium will have 10, and aluminum will have 11. So let me draw this out for you guys. So let's say this is the center, and we'll use blue for the electron shells. So 1, 2, 3, 4, 5, 6, 7, 8, 9. For magnesium, it's going to be the same, except there'll be one more electron here. But for aluminum, you're getting a completely different state, where it's going to look like this. And then we're going to draw the shells. 1 there, And then there's going to be a third outer shell. And then if I draw the crosses, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And where's the 11th one? The 11th one is out here. So look at the distance between this and the nucleus. So this is much greater. This distance is greater than this distance. So you're removing an electron from the third shell compared to sodium and magnesium, who are only removing an electron from the second shell. So we can see that the distance, or the ionic radius, matters more over here, because if you take a look at this jump, magnesium is the highest, and then it drops all the way to aluminum because it's trying to remove an electron from the outermost shell. So that's what we're going to write down in our answer. We're going to write that aluminum has an electron removed from a shell farther away from the nucleus. Thus, sodium and magnesium have a much greater ionization energy than aluminum. So, and the same principle stands for the other elements over here. So silicon is also having it removed from that third outer shell, from that third electron shell. Same for phosphorus, same for sulfur, chlorine, and argon. But the reason that these are sort of increasing is because, remember, the other thing we talked about is the nuclear charge. So nuclear charge is also increasing. Charge is also increasing. Whereas over here, you have, if we go down over here, these 9 electrons are being attracted by 11 protons. This is being attracted by 12 protons. So their nuclear charge is also high. Nuclear charge high. So not only do they have a short ionic radius, so both sodium and magnesium have short ionic radius, and a large nuclear charge, which is why they're the greatest between all these elements, and why it's more than aluminum. Very fun question. All right, so let's move on to the next one. And the third ionization of energy of argon, the ion produced has the electronic configuration 1s2, 2s2, 2p6, 3s2, and 3p3. So complete figure 1.3 to show the arrangement of electrons in the orbitals of this ion. So again, very simple. You don't have to worry too much about this. You know that each box can only contain 2 electrons, and remember, they have to have opposite spin. So it's not mandatory that you give it in this direction. It can also be sort of like this and this, but they have to have opposite spin. So in fact, I'll show it to you guys. So it can look like this. It can look like this. You just have to give, I'm sorry, that was a really poor one. Let me fix that. So it can also look like Sorry, very bad at drawing straight lines, it seems. Yeah, just horrible. And then like this, and again, it doesn't matter as long as they're showing that they have opposite spin. 3s, once again, it's going to be up one, and the other one will be down in the other direction. Now remember, it says 3p3. So for each one, you're going to draw one electron only. Because remember, if electrons can help it, then they will go in separate, they will not pair with each other. Because obviously they're negatively charged, so they don't want to be close to each other. So if there is space, then they will be separate from each other. But when there's no space, like take for example in 2p or in 3s, that's when they're going to be together. All right, so 1D, most period 3 elements react with oxygen to form oxides. Write an equation for the reaction of phosphorus with oxygen. This is a fun question. We know that phosphorus is in P4. So this will be P4. Remember, it's only 1 mark, so you don't need to worry about state symbols or anything. So you can just go ahead and write, let's say, O2, and you're going to get phosphorus 5O2, P4, and 5 2s are 10, so this will be P4, 10. Because remember, oxygen has a valency of -2, phosphorus has a valency of +4. So to find out exactly how many, let's say if you had, phosphorus exists as P4 as well, so you're going to have to put P4. So let's say you get it. Write an equation for the reaction of aluminum oxide with an excess of aqueous sodium hydroxide. So it's going to be aluminum oxide plus, again, it's only 1 mark, so you don't need to include state symbols, plus sodium hydroxide. And this is going to give you 2NaAlOH4. Simple. Sodium has a valency of +1, aluminum has a valency of +3, hydroxide has a valency of -1, so -1 plus that, and you get hydroxide. And yeah. So let's move on to our next question. Actually, this doesn't look right to me. 1 second. So aluminum, because then remember, a good trick is to find out where everything needs to be constant. So you've got 2 aluminum, 3 oxygen, 1 sodium, 1 oxygen, 1 hydrogen. But we got 4 hydrogen here. No. So this cannot be right. So let's erase this. Let me get a bigger eraser over here. And let's look at it again. So it's with an excess of aqueous sodium hydroxide. So because it's aqueous, it means that there's going to be water involved. So let's rewrite this again. So let's say Al2O3 plus sodium hydroxide plus, there's going to be water involved, H2O, and that's going to give us Al, 1 second, 2, it's going to give us NaAlOH4. So now we have to do the balancing act over here. So we've got 2 aluminum, so obviously this is going to have to be 2 over here. So automatically that puts 2 over here. And the one thing that we're missing is, so there's 2 oxygen. So now you've got a total of 5 oxygen, 6 oxygen over here, but you got 8 oxygen over here. So we're going to have to fix that. So if there's 5 over here, then to fix that, we just need to put a 3 over here. And there we go. This one was a bit more difficult, so hopefully you guys were able to get that. And if not, no problem. Just make sure you remember this when you go into the exam hall. All right, so we're moving on to our next question. The group 17 elements are oxidizing agents. Explain how group 17 elements act as oxidizing agents. So this is a fun question. So when they're talking about group 17, what they're really talking about is the group 7 elements. So let me just pull up the periodic table really quick. And remember that you'll always have the periodic table with you. So if I just go over here, put that there, and we go all the way down here. Flip this. So look, your group 17 elements are all the halogens. Group 17 basically means group 7. So because they're group 7, that means that in their outer shell, they have 7 electrons. So 1, 2, 3, 4, 5, 6, and 7. So keeping this in mind, an oxidizing agent is anything that oxidizes another element. So remember that oxidation is the loss of electrons. So the way I remember it is oil rig. So oil rig means basically oxidation. Oxidation is loss. And remember, this is all in terms of electrons, and reduction is gain. And these are all talking about electrons. So reduction is the gain of electrons, and oxidation is the loss of electrons. So if you're oxidizing another element, it means that you're taking away an electron, and so when you take away an electron from someone else, that's when you become reduced yourself. So then you're going to mention becomes reduced itself. So explain how group 17 elements act as oxidizing agents. So you're just going to mention the definition of an oxidizing agent, which is they take an electron from a reactant, and oxidize it while being reduced themselves. So there we go, 1 mark. Nothing too complicated, nothing too difficult. So as long as you mention that they remove an electron from a reactant, then you'll be fine. So now the next question is write an equation to show the reaction in which chlorine oxidizes aluminum metal. So aluminum plus Cl2. Remember, chlorine only exists in a diatomic state. So you're going to get aluminum. Aluminum has a +3 valency, so you're going to need 3 chlorine because chlorine has a -1 valency. So let's take a look. We need to balance this out. So you've got 2 chlorine here, but 3 chlorine over here. So the HCF of, the LCM of 2 and 3 is going to be 6. So you're going to put 3 over here, and automatically a 2 comes over here. And aluminum, because it's single state, you can add whatever you want over here. So this will be 2. There you go, 1 mark, very easy. A student heats equal amounts of iodine and hydrogen in a sealed flask. The student leaves the contents to cool. State what you would observe during the reaction. So iodine is, we don't really have purple here, so let's do this. So iodine is purple in color. But the reaction that happens is H2 plus I2 gives you 2 hydrogen iodide. And this is colorless. So as you're forming hydrogen iodide, you'll notice that the purple color, or you can write gas, slowly disappears. So chlorine and bromine can each react with ammonia to give nitrogen and a hydrogen halide. So then they give sort of the generic reaction, which is 3x2. So X over here can either be bromine, or it can be chlorine. So this is sort of the generic reaction. You don't have to worry about that. Plus 2 NH3 to give N2 plus 6 H and X. And again, X can be Cl or bromine. So let's mention over here. X is equal to Cl or bromine. The relative bond strengths of XX and HX determine the difference in the enthalpy change of the two reactions. Describe and explain the difference in the XX bond strengths of chlorine and bromine. So this is interesting. So let's take a look at the proton numbers for chlorine and bromine. So chlorine has an atomic number of 17, bromine has an atomic number of 35. So what that means is, if this is the chlorine nucleus, then you have, let's say, the 17 electron shells. So you're going to have 2, 8, and then over here you're going to have 7. So the distance between chlorine's nucleus and the last outer shell is this. And if you look at this for bromine, bromine has a 35. So this will be 2, 8, another 8, that's 18. 18 plus 8 is 26. 26 plus 8 is 34. And then you're going to get the final electron. So look at how much further this last electron is from the nucleus compared to chlorine. So because the valence shells are farther from the nucleus, there's less overall overlap. So what this means is, like, let's say if there's 2 chlorine nucleuses over here, then they're 7. So let me use different colors. So let's use blue. But they're both chlorine. So this is going to be chlorine, and this is going to be chlorine. So this outer shell electron and this outer shell electron are overlapping. And so there's more attraction. So this is being attracted with this and with this. And as for this one, it's being attracted by this one and also by this one. So there's more attraction as more overlap. Whereas if you take a look at bromine, so if I draw the same thing, bromine's one is already far from, so let's assume it's somewhere over here, and let's assume that you can't even see that, so this one will probably be somewhere over here. So it's already far from the nucleus, right? So there's less overlap. So that's what we're going to write in our answer. That the Br bond is weaker as the valence shells are farther from the nucleus in bromine, and so there is less overlap and less attraction compared to chlorine. Compared to chlorine. There we go. So simple, but you just need to be able to explain it more. The bromine-bromine bond is weaker. Maybe we need to mention over here as bromine is a larger molecule. So the valence shell electrons are farther, and thus there's less overall overlap. between the two molecules. Describe the relative thermal stabilities of hydrogen chloride and hydrogen bromide. So again, we just mentioned that the bromine-bromine bond is weaker. So that would stand to reason that the hydrogen-bromine bond would also be the same. So let's say, for example, this is hydrogen, and hydrogen only has one electron over here. And let's say chlorine will be over here. So this is the last one. Still closer compared to that, but if we do it for bromine, where you've got, let's say, hydrogen over here, and its electron, and bromine would be all the way over here. So that's significantly farther, right? So you're going to write HCl is more stable. All right, so let's move on. Definition. All right. Definitions, very easy marks. Let's be sure that we don't make any mistakes when we're solving this, because these are marks that are very easy and we can't afford to lose these. So I'm just going to write it. There's nothing to explain over here. The enthalpy change when 1 mole of a compound is formed from its constituent elements in their standard states. So I'm going to use a different color to highlight which one is 1 mark. So this is going to be 1 mark. 1 mole of a compound is formed, and the other mark is for in their standard states. So as long as you're writing these two, you're going to get your 2 marks. You also have to mention the enthalpy change, obviously. Not necessary, but you know. So table 2.1 gives data relevant to the reaction of chlorine with ammonia. So ammonia, when it's formed, it releases. So negative means that it's releasing energy. Releasing energy, which means that it's exothermic. So ammonia releases 46 kilojoules per mole, and hydrogen chloride releases 92 kilojoules of moles. So use the table data in table 2.1 to calculate the enthalpy change of the reaction of chlorine with ammonia. So do we have any reaction of chlorine with ammonia? Yes, so it's over here. 3x2 plus 2NH3 gives you N2 plus 6H. X. So since it's chlorine, let's write down the thing. So it's going to be 3Cl2 plus 2NH3, which gives you N2 plus 6HCl. So the enthalpy change of the reaction. So del H is equal to bond formation minus bond breaking. So let's find out what bond formation, what energy is released in bond formation. So for bond formation, you're going to have 6, you're going to have HCl being formed 6 times. So this will be 6 into minus 92. And what about for bond breaking? So you're breaking a ammonia bond 2 times. So this will just be, let's use yellow for this. This will just be 2 into minus 46. So together, your bond formation will be 6 into minus 92, which is minus 552. Minus, and remember, this is still negative, so this will be 2 into minus 46, which is minus 92. So what this actually is minus 552 plus 92, which comes out to minus 460. So we'll write over here minus 460. Iodine reacts with ammonia to form Ni3. Predict the shape of a molecule of Ni3. Explain your answer. So nitrogen is in group 15, so it has 7 outer shell electrons. So 1, 2, 3, 4, 5, 6, 7, which means that it can take in 3 more electrons. So because it can take in 3 more electrons, the way that this will go is, let's say if I'm using yellow for iodine. So this is an iodine molecule, and it's going to share 1 electron here. Let's say you've got 1 over here, and there's going to be 1 iodine, so it's going to be over here, and you're going to have 1 iodine over here, and it's going to give you 1 electron here. So this shape has 1, 2, and let me just do that better. 3 bonding pairs. 3 bonding pairs and 1 lone pair. 1 lone pair. So whenever anything has 3 bonding pairs and 1 lone pair, it forms a It forms a pyramidal shape. Pyramidal. So we're going to write exactly that. Pyramidal. It has 3 bonding pairs and 1 lone pair. Table 2.2 shows some information about the reactions of sodium chloride, sodium bromide, and sodium iodide. So they say what happens when it's reacted with silver, what happens when it reacts with sulfuric acid, and what happens when it reacts with, what do you see? So one is what type of reaction, but this is already filled up, so we don't need to worry about that. And what are your observations? So observation is what you see, smell, or hear. So keeping that in mind, let's move forward. So observation, again, it's the same thing over here. What you see, smell, or hear. So when you add silver to sodium chloride, you're going to get silver chloride. Over here, you're going to get silver bromide, and you're going to get silver iodide. So this is part of the salt test sheet that you guys have in paper 3. So I'm not going to go over this too much. In bromine, you're going to have a cream PPT. And for iodine, you're going to have a yellow PPT. Yellow PPT. So whenever you add concentrated sulfuric acid, you're going to get sodium sulfate. This will be, this is also going to be sodium sulfate. So you're going to keep getting sodium sulfate. And so what's being liberated is the chlorine and the bromine. So because both chlorine and bromine are being liberated, we know that chlorine is, it doesn't really have any color, right? So it's sort of like colorless. Whereas bromine is brown. So we're going to mention for the answer is fizzing for both of them. But for sodium chloride, we're going to mention that you see steamy fumes. And for sodium bromide, we're going to mention a brown liquid, which is, of course, your bromine. So moving on is suggest an identity for the species that produces each observation in the reaction of sodium iodide with concentrated sulfuric acid. So there's a lot of reactions that are happening whenever you react sodium iodide with hydrogen, with sulfuric acid. So let's write them down. So sodium iodide plus H2SO4. You're going to get NaHSO4 plus hydrogen iodide. So this continues on. So this hydrogen iodide then reacts with hydrogen iodide plus sulfuric acid. And that's going to liberate iodine plus sulfate ions plus water. Now here's the fun thing. When you have more, hydrogen iodide, it's eventually going to react with more, so let's say over here 8Hi plus H2SO4, which is going to give you H2S plus 4H2O plus 4 iodine. And then this H2O that's being produced, so over here, this H2O, this is going to react with, sorry, one second. There's a lot of reactions basically happening, but all you need to know is that the black solid is your iodine, your yellow solid is sulfur, and the effervescence is hydrogen iodide. So black solid, iodine, yellow solid, sulfur. The sulfur is produced when H2SO4 reacts with 6 moles of hydrogen iodide, which releases 3I2 plus sulfur plus 4 H2O. And effervescence is going to be hydrogen iodide. Hydrogen sulfide, sorry. This one was a bit of a tricky question, but hopefully you guys were able to solve this one. So yeah, let's move on. Table 2.3 gives some information about magnesium chloride and silicon chloride. So magnesium chloride conducts electricity when dissolved in water, and it conducts electricity when liquid. Sodium chloride does not conduct electricity when liquid, and it has a vigorous reaction when added to water. So now they're saying explain the difference between the electrical conductivity of liquid magnesium chloride and of liquid silicon chloride. So it all goes back to the first question that we answered over here, right? Where we looked at the metallic bonding of magnesium chloride. So they have, let's talk about metallic bonding. So now we're at ionic bond. So the ionic bond is sort of similar to the metallic bond, where they have mobile ions. So because they have mobile ions, they're able to conduct charge. But sodium chloride doesn't have any of that. So magnesium chloride is an ionic compound, whereas silicon chloride is a covalent compound. So ionic compounds have mobile ions, and covalent compounds do not. So when liquid, the ions in magnesium chloride become mobile and are able to move and conduct charge. Move and conduct charge. Whereas, if you look at silicon chloride, it's covalent and doesn't have any mobile ions and conduct charge, and are able to move and conduct charge. But SiCl4 is a covalent compound with no ions to conduct charge. There we go, very simple. So magnesium chloride, what happens when each chloride is added to water? So MgCl2 plus H2O. So this is going to form magnesium hydroxide, and you're releasing chlorine and there's hydrogen, so you're going to get 2 HCl. So this is an alkali, this is an acid, so alkali plus acid equals neutral. So the pH will be 7. Whereas for silicon chloride, this is going to be SiCl4 plus H2O, which is going to give you silicon hydroxide plus 4HCl, which is an acid. So the pH can be anywhere between 0 to 3. So you can put anything. Let's say it's going to be 3. Nice. Very easy 22-mark question. Hopefully there wasn't anything too complicated over here. It was pretty simple. A good mixture of a bunch of different questions. Hopefully you guys were able to solve this without that much trouble. So we're moving on to the organic chemistry portion of the paper. So the question is, cycloalkanes show similar chemical properties to alkanes, but have the same empirical formula as alkenes. So define empirical formula. Again, this is a definition. I don't want to waste too much time on this. But basically, if you can simplify something, so this would be C2H4O. That's the simplest ratio. And that is the empirical formula. So you're going to write simplest ratio of each element in a compound. All right, cyclopentane has 4, okay, this is important. Remember, it says cyclic structural isomers. One of these isomers is C, shown in figure 3.1. Complete figure 3.1 to show 2 other cyclic structural isomers. So remember, you can go drawing alkanes or alkenes because they are not cyclic. So no alkanes, no alkenes. Because the question specifically asks for cyclic structural isomers. So for this, you can go a bunch of different ways. For example, you can draw sort of a square, and from this square, or more rectangle in this case, boom. So 1, 2, so let me mark them with this. So 1, 2, 3, 4, and 5. Another one that you can do is maybe like a triangle, sort of following this one over here, and then one over here and one over there. So that'll be 1, 2, 3, 4, and 5. Remember, you don't have to count this because it's already been counted there. So that's going to be your cyclic structural isomers. Cyclopentane reacts with chlorine in the presence of ultraviolet light to form C5H9Cl. So now the question is saying the reaction is initiated by the bond fission of chlorine. State the type of bond fission shown in the initiation step. So whenever you're having a bond fission of two equally polar molecules, so in this case it's chlorine, and they both have the same electronegativity. Same electronegativity. So because they have the same electronegativity, when they split, they're going to split evenly. So this is known as homolytic, because they both share the same number of electrons. So it's split between them equally. But if you're talking about heterolytic, then that's where you get a carbocation, and that's where you get a nucleophile. So you're going to get an electrophile and you're going to get a nucleophile, because one of them is going to be left without an extra electron, and the other one's going to be left with an extra electron. So it's interesting. So we're going to write over here, very simple, nothing too complicated. This is going to be homolytic. And you've probably already studied these reactions before, so I'm not going to go too in depth to them. Complete the equations to show two propagation steps. So this is propagation. Remember, you cannot show termination. So a lot of you might be tempted to write C5H9 radical plus Cl radical, and then you're going to get C5H9Cl. But this is wrong. This is a termination step. Oh, which is sort of the question for this one over here. So for this one, you need to keep showing that it's propagating. So you're going to show there's going to be another chlorine molecule, and you're going to get C5H9Cl plus a chlorine radical. So this is, again, let's say there's a chlorine radical, and then you're going to get C5H9 plus HCl. I've already answered this one, so this is going to be termination. All right, moving on. Figure 3.2 shows a reaction cycle involving cyclopentene and C5H9Cl. So the first question is asking, identify a suitable reagent for reaction 3, where we're turning cyclopentene into C5H9Cl. It's very simple. This is going to be HCl. Now the interesting question. Use the data in figure 3.2 and table 3.1 to calculate the enthalpy change of reaction 2 del H2. So the way this goes, first of all, we're going to have to figure out what the enthalpy change of combustion. So we have the enthalpy change of combustion for cyclopentene, and for hydrogen. So let's label this down. Cyclopentane. This will be cyclopentene. And that's hydrogen. So if you look at this over here, to get to reaction 3, you need to go through reaction 1, and then you need to go to reaction 2. So del H3 is equal to del H1 plus del H2. In the same vein, they're asking us to calculate the enthalpy change of reaction 2. So del H2 is actually, if you rearrange it, del H3 minus del H1. So we already have del H3. Now we need to calculate the reaction 1 when cyclopentene reacts with hydrogen. So you're combusting cyclopentene and hydrogen. So this is going to be minus 3115 plus minus 286. So I'm going to write over here del H1. So this will be minus 3,292. So this, sorry, that isn't your del H1. This is actually, well, no, we'll just write this down. So this is actually going to be your combusting. So this is your reactants. Now let's take a look at the products. So for products, you're getting cyclopentane. So cyclopentane is giving you minus 3292. Minus 3292. So del H1 is equal to reactants minus product. So this is how much energy it's going to absorb. So let's take a look. So that'll be minus 3292 minus. Oh, sorry. I think I accidentally copied this one over here. So let me just put this into a calculator. Minus 3115 minus 286. That's minus 3401. Minus 3401. So this will be minus 3401 minus 3292. And if you do the math, that's going to be minus 3401 plus 3292 because minus minus. And so you get minus 109. So now if you go back up, it says del H2 is equal to del H3 minus del H1. So del H2 is equal to minus 53 minus 109, which is minus 53 plus 109, which is equal to plus 56. So remember, the sign is very important. This will be plus 56. There you go. Very simple. Nothing too complicated. And yeah, let's move on to the next question. Cyclopentene, C5H8, reacts with hot concentrated acidified potassium manganate to form compound W. So draw the structure of W. So cyclopentene, if I were to draw it, looks something like this, 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 and then this. And then you've got your double bond over here. So acidified potassium manganate will oxidize this, and you're going to have an OH added here, and double over here. You have an OH added here, and a double over here, and this will open up the structure. So it'll look something like 1, 2, 3, 4, 5. Give an OH over here, give a double over here, give a OH over here, and a double over here. Because what this is doing is sort of breaks the double bond. Very simple, and yeah, let's move on to the next question. The infrared spectrum of W. So this is W, the one that we've done over here, is shown in figure 3.3. Identify two absorptions in the infrared spectrum of W that would not be present in the infrared spectrum of cyclopentene. Write 1 or 2 in figure 3.3 against each of these two absorptions. Complete table 3.2 to show which bond is responsible for each absorption that you've identified in figure 3.3. So cyclopentene, this is for W. So W means this compound over here that we just drew. So over here we can already tell that you're going to get a double O bond and you're going to get a hydroxyl bond. So let's take a look at where we're going to find this CO, the carboxyl or the carbonyl bond, between 1640 to 1670, and so any one of these ranges. So let's take a look if we see anything between any of this. So 500, 600, 700, 800, 900, 11, 12, 13, 14, 15, 16, 17. Look, there's a dip over here. So this is going to be your C-double-O bond. And the other one, we're looking for OH. So OH is the carboxyl bond, which is between 2500 to 3000. So if we look at 3000, there's a dip over here. So this is responsible for OH. So we're going to put down very clean the OH, and then you're going to write C-double-O. And over here we're going to write sort of which one is responsible. So remember, there's two things that you have to do over here. Number one is write down which one the bond is responsible for, and then you have to write 1 over here. So you're going to write 1 over here, and you're going to write 2 over here. So this is very important. This is why you read the question. Write 1 or 2 on figure 3.3 against each of these two absorptions. So that's what this is all about. Writing 1 and writing 2. And there we go. That's the third question done. We're down to our last question. So let's see what it says. The reaction between sodium Na2S2O3 and hydrochloric acid is monitored at a constant temperature. And it shows that when you react it with hydrogen chloride, you get sodium chloride plus sulfur dioxide plus sulfur and water. So figure 4.1 shows the concentration of hydrogen chloride varies with time. Use figure 4.1 to find the average rate of change of concentration of hydrochloric acid in this reaction between 0 to 100 seconds and between 400 to 500 seconds. Include units in your answers. So let's take a look. At 0, add 0, your concentration is 1. And at 100, your concentration is 0.5. So final minus initial divide by time. So let's go up, so let's go down and write that down. So 0.5 minus 1 divide by 100 is going to give you 0.005. And remember, our time, so this is going to be concentration divided by time. So concentration is mole per dm cube, and time is in second minus 1. So this unit will be mole per dm cube second minus 1. Mole per dm cube second minus 1. This will be the same for both. Mole per dm cube second minus 1. So this will be 0.005. And now what about for 400 to 500? So they're both the same over here. Take a look. So if your initial is equal to your final, initial equal to final, so this turns out to be, so let's say this is around 0.1 over here. So this is around 0.12. So 0.12 minus 0.12 divided by 100 is equal to 0 over 100, which is equal to 0. So this will be 0. So use figure 4.1 to identify the limiting reagent and explain your answer. So look, you still have a concentration of hydrogen chloride. If the concentration of hydrogen chloride reaches 0, then you could say that hydrogen chloride was the limiting reagent, but not concentration never reaches 0. So, not limiting. Instead, because the concentration becomes constant, you can say that the reactant, what do you call it? So since hydrochloric acid is reacting with Na2S2O3, you can say that that is the one that got used up. So if we go down, the limiting reagent will be Na2S2O3 as the reaction stops before all the HCl is used up. Very simple. Explain why the rate of reaction changes with time. So as you'll notice, as the concentration decreases as time increases. So because the concentration is decreasing, you're having less effective collisions happening. So let me go down to over here. So let's say at 10 seconds, I'm going to denote Na2S2O3 with these red balls. I'm going to denote hydrogen chloride with these X's. So 10 seconds, you have something that looks like this. And you have this. So what's happening is there's more molecules as more concentration, more collisions, and so more effective collisions. More effective collisions. Whereas if you take a look at this at, let's say, 350 seconds, that's when you've probably got maybe one. And maybe you've got, oh, I messed up. So let's say you've got maybe two. And you've got one of this. So what's happening here is that there's less molecules as concentration decreased. So less collisions and therefore less effective collisions. Very simple. So in our explanation over here, we're going to write that concentration decreases number of collisions decreases, so actually let's not put that there. Therefore, the number of effective collisions decreases. Effective collisions decrease. All right, so let's go to the next question. The reaction between Na2S2O3 and hydrochloric acid is repeated in a second experiment. In this second experiment, 25 cm cube of 0.05 mole per dm cube Na2S2O3 reacts with 0.002 moles of hydrochloric acid. Calculate the number of sulfur atoms produced. What a question. So if you remember, 1 mole has Avogadro's constant, which is 6.02 into 10 to the power 23 atoms. So now we need to figure out what the concentration is. Concentration times Avogadro. Very interesting question. So this will be N is equal to 25 by 1000 times 0.05. If you do the math, you're going to get 0.001, which you're going to multiply with 6.02 into 10 to the power 23, which is going to give you 6.02 into 10 to the power 20. It's going to recheck, make sure that I'm not writing anything wrong. 25 into 1000 into 0.05, 0.001, yeah. This into 6.02 into 10 to the power 23. Yeah. So 0.001. Yeah. 6.02 into 10 to the power 20. Hopefully you guys were able to solve that. And yeah, explain why the rate of reaction cannot be monitored accurately by measuring the volume of sulfur dioxide produced. So if you take a look at the reaction over here, you have SO2 plus H2O. So these two will end up reacting with each other. Reacts with each other. So that's why you can't measure that. So this will be SO2 reacts with the H2O. And here we go. Here's the last bit. Figure 4.2 shows a possible arrangement of outer shell electrons in one SO2 molecule. So use figure 4.2 to predict the shape and bond angle of a molecule of SO2. So if we take a look at this, what are we noticing over here? We're noticing that there's 1, 2, 3, 4 bonding pairs, and then you have 1, 2, 3, 4, and 5 lone pairs. So keeping this information in mind, and probably recalling from previous lecture materials, the shape of this is going to be non-linear, and you can put in any value between 120 to 116. So I'm going to put the one that's in the middle, 118 degrees. And the last question, use table 4.1 to predict the strength of the dipole moment of SO2, if any, compared to that of H2O. So let's take a look at the electronegativity difference between SO2 and H2O. So for hydrogen and oxygen, so let's say OH, it's going to be 3.5 minus 2.1, which is around 3.5 minus 2.1, 1.4. And what about for SO2? So let's say SO, this will be 3.5 minus 2.6, which is 0.9. So 1.4 is greater than 0.9. So as a result, you're going to mention that SO2 has the weaker dipole moment, as the electronegativity difference is less. negativity difference is lower than H2O's. And then you can sort of give figures 0.9 in SO2 compared to 1.4 in H2O. And there we go. That's the entire paper. So yeah, if you guys have any questions at all, please feel free to reach out to us. I feel like this is a very good, this is a good test of sort of all the concepts you've learned throughout AS. And if you guys try hard and you don't panic and you give it your absolute best, I have a feeling that you all are going to do well. So believe in yourself. You've made it this far. You're going to get even farther. And yeah, best of luck. Remember to answer all questions and just believe in yourself. So this has been Albab, and I hope you guys learned something. If you have any questions, feel free to reach out. Thank you for watching, and see you next time.